see what are the solutions. In theory, we can solve this kind of problems. For instance, in our calculus course, we are required to find minimization problem by taking the first order derivative and let it to 0 and then solve it to find x1. This could be a minimum or maximum point. And then we have to take the second order derivative to the function and see whether it is a minimum point or a maximum point. So this kind of solution can be converted into the solution of equations. And even more than that, we have to take the second order derivatives, which increase our burden. So what we need to do is to avoid the theoretical way to solve problems. We should here concentrate on how to solve this kind of problem with Matlab. We do not necessarily have to know the details, the technical details for how to solve it in low-level programming. What we need to do is how to solve it using a Matlab command rather than the technical details of it. To solve a minimization problem, what we need to do is to call a function called fmin search function. It is provided in Matlab, but you have installed Matlab. You do not have to install any other toolboxes. You can use fmin search to find minimization of a given objective function. And again, this function can be described like .m file or an anonymous function. It is similar to the case in equation solutions. And also, we have to specify an initial search point. I shall explain that one later on to you. And by coding this function, we can find x, which minimizes the original function. If it is successful, then we can find x. If you have installed the optimization toolbox, which is a product also of Matlab, then you can use another function, fmin unc, which is more efficient than this one. So you can use these two functions. And the simplest statement to code functions are something like this. We have to specify the objective function, initial search point, and normally we should have the results. If we cannot get the result for some reason, then we may get some error message or warning message. So this is the simplest way to solve a minimization problem. And these two functions can be called in a more complicated way like this. We have to specify the objective function initial searching point, and also we can specify the control components. I have explained this one to you earlier on equation solutions, which contain some specifications on this point, and for optimization problems there are more specifications. So we can use this kind of notations. And also we can use extra variables, but I'm not going to talk about this one too much here. For the retained variable, we can not only return x, which is the solution to the problem, we can also have f, which is the minimized value of objective function. And also we should obtain a flag. If the value of flag is greater than 0, they say that the optimization is successful. Otherwise, it fails. So we can use this one to find more information of the optimization process. And also we can find other information. I will show this one through examples. And the two functions can be called in the same way. One is with Matlab, the other one is should come with an extra toolbox, the optimization toolbox, but it is more efficient. So now let's consider the problem. Suppose we want to have a two-dimensional function like this. So our question is, what is the minimum of the function? In other words, select what kind of values for x and y which makes the function z the minimum. To solve this problem, again, like equation solver, we have to specify variables to compose an x vector. For this example, we have to assign x1 equals to x, and x2 equals to y, and again, x should be a vector. This is the first thing we have to do. The other thing is we have to rewrite the objective function. We have to change x to x1 and y to x2, so we can express the original objective function in this way. And then we can select an initial point. And then we can use this command to find the solutions. First, write out the objective function, select the initial point, and then solve the problem. So this is the final result. We can assign the display component of the control function OPT to ITER, and then we can display some of the intermediate results. And we see that the objective function is decreasing like this, and finally it will settle down on a certain point, which means that the solution is successful. Now let's try another function. And it is seen that we will only use less iterations. So I say that the optimization toolbox function is more efficient in solving the same problem. The results are virtually the same. To let you understand better the optimization problem, let's see the illustration here where I got the data, intermediate data from the program. This is the initial point. Then by searching, it will select this direction first. And the direction is selected by the gradient of the function, numerical gradient of the function. And find this point. And then find this point. And finally settle down here, which are the solutions to the original problem. Normally, we do not have the intermediate result. You have to modify the original equations optimization problem solver to retry this kind of result.